welcome to part 4 in our unit on circuits. In this part, we're going to be introducing Kirchoff's rules, which are a way of analyzing slightly more complex circuits than we can do with equivalent resistance. So without further ado, here are Kirchoff's rules. Sometimes you will see these referred to as Kirchoff's laws. It seems to depend on which book you look at. Okay, so slightly more complicated circuits. More than one battery, really, is what it comes down to. Junction rule. At any junction, the sum of the currents entering the junction equal the sum of the currents leaving that junction. We've already discussed this rule, but we didn't really formally name it. And that discussion was back in part 1 of this unit. The second rule is the loop rule. The change in potential around any closed loop path in a circuit equals 0, which is kind of a nice way of saying that whatever the battery provides in terms of energy or potential has to be used by the elements of the circuit. Okay, examples coming. But the first thing I want to emphasize is that when you're working with Kirchoff's rules, particularly the loop rule, direction matters. So I'm going to give you the rules for the directions and how you apply them, and then we'll do lots of examples, and it's, pick your way of doing it. I can give you the rules and then do an example, or I can give an example and just kind of apply the rules without formally giving them to you. Either way, you got to learn them both. Okay, so the first thing is we have a battery in a circuit. So remember, the long edge of the battery is the positive edge. So when you draw your loop, if the direction of the loop crosses through the battery from the negative terminal to the positive terminal, then when you write your equation from the loop rule, this battery will contribute a positive voltage to the circuit. Contrast that with if you have the battery facing the same direction, so positive is still on the right, but the loop goes the other direction, then this battery contributes a negative voltage to your loop equation. With resistors, you have a similar sort of rule. So what you need to compare here is the direction of the current flowing through the resistor to the direction of the loop. And if those two things are in the same direction, then that resistor is using energy, so you add a negative voltage. But using Ohm's law, we know that that will be a negative IR added to the equation. On the other hand, if you have your current in one direction and your loop going opposite the current, then when you write your loop equation, you add voltage. So V equals IR. Okay, so those are the direction rules, if you will. Let's now do a very, very simple example where I show you how this works. And for that simple example, we are going to do a circuit with just 2 parallel resistors. This analysis is almost the equivalent of using a sledgehammer to pound in the nail to hang a very small picture frame. It's complete overkill, but it works, and it's good for the illustration. So let's let the battery have a potential of V. Let's call this resistor R1, this resistor R2. Okay, step 1 when doing a Kirchoff rule problem is to define your currents. Oh, I can't spell currents today. Here we go. So step 1 is to define the currents. Make a choice. It doesn't matter if you choose correctly or not, because assuming that you choose are self-consistent and can manage the algebra that comes with it, if you've chosen incorrectly, you'll come up with a negative sign. And you just say, oh, look, I chose incorrectly. It goes the other way. And it works out in the end. Sometimes it does help to give a little bit of attention to the circuit and give a little bit of attention to the circuit and make an educated guess, if you will. But sometimes it's very not obvious which way it should go. Okay, so I'm going to define the current coming out of the battery. I wrote a 1 here, but I just want to call this a generic I. At the junction, it's going to split, and I'm going to let I1 go through R1 and I2 go through R2. Okay, so I've got my currents defined. Step 2 is the current rule. Okay, so if I look at this junction, I have I coming in, I have I1 and I2 leaving. So I keep writing that 1 and I don't want it there. I1 plus I2. Okay, so I equals I1 plus I2. If I look at the other junction, I see that I have I1 coming into it, I have I2 coming into it, and I would have I leaving it, and I would get the exact same equation. Current in equals current out. Okay, step 3 is define your loops. Okay, what is a loop? It's a closed path around a circuit. For this circuit, there are 3 possible loops that you could choose. So I'm now going to show you what those 3 loops are. And for this, I'm going to use 3 different colors. So the first one starts at V, goes through R1, and comes back to the battery. Loop 2 starts at the battery, goes through R2, so it goes all the way around the outside edge and comes back to the battery. And the last loop runs over here, so through R1 and R2 and back around. Okay, so that's step 3. On to step 4. Step 4 is the voltage rule. With the voltage rule, we take and we add up, following the sign conventions I just gave you, all the voltages around a loop. Different physicists, different people like to do this slightly differently. My preference, if I can, is to start and stop at batteries. Other people like to start and stop at junctions. The only thing is that you have to start and stop at the same place in your circuit. Okay, since I color-coded my 3 loops, I'm also going to color-code my work in this with the same color. So I'm going to do the purple loop first. Starting at the battery, I look, and this loop goes up through the battery from the small end to the large end, or from negative to positive. So that battery contributes a positive voltage to my circuit. I follow I around. At the junction, I turn and I go down through R1, and my loop is in the same direction as my current. So I subtract off the voltage due to, or the voltage used by this resistor, which is minus I1 R1. I then hit the second junction, turn and go back to the battery. I'm now back to where I begin. Since I'm back to where I begin, I let it equal 0. Okay, on to the blue loop. Okay, so again, I'm going to start at the battery. I'm going to go V. Again, I'm going from small edge to large edge, so it's positive. At the junction, I go straight, which heads me down through R2 in the same direction that I2 is moving. So my current is going downward and my loop is going down through it. So I subtract off a minus I2 R2. Once I clear the resistor, I come around, I hit the second junction, and then I proceed back to the battery. Since I'm back where I started, I let it equal 0. And for the last loop. Now, the last loop does not have a battery, so I can't start or stop at the battery. Okay. So what I'm going to do is I'm actually going to start at the lower junction, because that's the direction my loop is going. And the first thing I'm going to do is I'm going to head up through R1. So the green loop is heading up through R1, but look at my current is going down. The loop is up, the current is down. Therefore, by the sign convention, I add in that voltage. So I add in I1 R1. At the junction, I turn and take the right and follow I2 down through R2. So for I2, my current and my loop are in the same direction, so I subtract. Okay, those are my 3 loop equations for this circuit. When you're solving Kirchoff rules and Kirchoff or Kirchoff law problems, you need one more equation than you have branches. This particular circuit has 2 branches, one with R1, one with R2. Therefore, to fully solve this, I need 3 equations. In order for it to work, the 3 equations you choose have to include this one. So this one's a must. And then from your other lip, oh my goodness, from your other set, in this case, we're going to choose 2. I need 3 equations. I have to choose the current rule 1. Therefore, I need 2 more from down here. So now you're like, okay, well, which 2 do I choose? It doesn't matter. If you look at these, you will see that if I take the blue equation and the purple equation and solve them simultaneously, I end up getting the green equation. These 3 equations at the bottom, purple, blue, and green, are not linearly independent. I can get one by combining the other 2. Therefore, it's not going to make a difference which 2 I choose. Okay. So now we're going to keep going here, and we're going to solve this. Okay. So the first thing I'm going to do is use I equals I1 plus I2. I then have V minus I1 R1 equals 0 as one of my 2 loop equations, and V minus I2 R2 equals 0. Now this is a very easy set of equations to solve, because I can find the value of, say, I1 by solving this equation. So I1 will equal V divided by R1. And similarly, I2 will equal V over R2. Now I can take these 2 equations, plug them in over here, and I get I equals V over R1 plus V over R2, which, if you look, is V times 1 over R1 plus 1 over R2. But this is the equivalent resistance for 2 resistors in parallel that we learned previously. Along the way, I said we would derive that formula. We just derived it for 2 resistors. So I could write this as V over the parallel resistance, which is what we know this particular circuit should give as the current being produced by the battery. Okay, this concludes this example. It concludes this part. In the next part of this unit, we are going to do a slightly more complicated circuit, and I'm actually going to work it twice, showing you again how the sign conventions work and different routes through the algebra.